in this video, we will talk about fuzzy regression discontinuity designs. This is the most general regression discontinuity design. In essence, we can see the sharp regression discontinuity design that we've seen in the previous video. We can see this as a special case of the fuzzy regression discontinuity design. So a regression discontinuity design is based on the idea that the probability of getting treated jumps at that discontinuity. The discontinuity is typically an arbitrary threshold where it's difficult for units to select into treatment status. That's what makes regression discontinuity such an attractive method for causal inference. And in a sharp regression discontinuity, the jump in the treatment probability is between 0 and 1. In a fuzzy regression discontinuity, it jumps but not between 0 and 1. Okay? So all it does here is that the probability of treatment jumps at that discontinuity of x naught. And what that amounts to is it comes down to it being an IV estimator. So it's an IV estimator because you have imperfect compliance with the treatment assignment. So people above the discontinuity are offered the treatment, but whether they take it, that's up to them, and not everyone will take it. But even people below the discontinuity can take the treatment, but they're not offered it or they're not encouraged. Okay? So the treatment probability then may jump at the discontinuity if we have a strong first stage, if units comply with the assignment that is done by the discontinuity. And that mechanically then works like an IV estimator. There is a difference relative to IV estimators in terms of the interpretation, because obviously when we run a standard IV analysis, we don't quite know who the compliers are and from what part of the population they come. Now, neither do we exactly know who the compliers are here, but we can obviously narrow down the population that has been encouraged to take the treatment very close to that discontinuity. So in that sense, it is technically an IV estimator, but we can learn a lot more about the treatment effect because the local average treatment effect we are estimating here, we know very much what that local in the local average treatment effect actually refers to. So the way we estimate a fuzzy regression discontinuity design, or we estimate the treatment effect in a fuzzy regression discontinuity design, is shown here, where we have T being the discontinuity, and then we have D the treatment. And we have an often hypothetical first stage, which is that the treatment is a function of observable characteristics and the discontinuity, whether you're above or below. I write here hypothetical because in many cases, in many applications, you will see that we actually either don't observe the actual treatment status, or the actual treatment status is not that interesting. Again, that is very different from most standard IV applications. So you will see a lot of fuzzy regression discontinuity designs where the reduced form that you see here at the bottom, namely the regression of the outcome on the discontinuity and the dummy, whether the person is above or below the discontinuity, where you see that regression estimated. And that parameter beta, the reduced form parameter, is in and of itself interesting enough. To give you an example, you see a lot of regression discontinuity estimates that show that getting into a better school has an effect on students' outcomes, or does not have an effect on students' outcomes. But if it does, then obviously you could think, well, what is it about better schools that gives these people the advantage? Is it that they have better teachers? Is it that they have better peers? Is it that they have more funding and do better activities that prepare them better for their later life? Or is it a combination of both? And if you see any of those intermediate channels, teachers, peers, other things, as the treatment, then obviously we cannot pin down which of those treatments it actually is. And that's why we actually typically see then the main regression being the reduced form, that person got into a better school or not, and then maybe we uncover through additional regressions, we try to say, okay, which of these channels is more likely to drive the result. That's how it's typically done in practice. Okay, but theoretically, we have a first stage and we have a reduced form. And if we have those two, and we then estimate the effect again within a bandwidth around the discontinuity, we have a Wald estimator. So in the sharp regression discontinuity design, you have a perfect correlation between the dummy, whether someone is above or below the discontinuity, and the actual treatment, and therefore the first stage equals 1. So those that term here in a sharp regression discontinuity design would be 0, and that one would be 1. In a fuzzy regression discontinuity design, that is not the case, because being above or below just shifts a fraction of the units into treatment, and that is reflected in the first stage. And then it's that the estimator for the treatment effect follows the exact same logic of the local average treatment effect that we've learned in when we talked about instrumental variables. And so it's the difference, the average difference in the outcomes that we can attribute to the difference in the value of the instrument. That's the reduced form, that's the numerator, and we scale that up by the likelihood of taking the treatment when being above the threshold, above the discontinuity, or the change in the likelihood of taking the treatment from going from below the discontinuity to above. Also, it's a standard Wald estimator. Now, one thing you need to be aware of is that a fuzzy regression discontinuity design becomes a lot more tricky when you look at it with interaction terms. Why would you do that? Well, the same reason why you would include interaction terms in a sharp regression discontinuity design, simply to allow for different curvature above and below the discontinuity. What you would need in order to estimate, then to have that Wald estimator, and if you do this with a two-stage least squares approach, is that you would not only need to have an instrument for the treatment, but you would also need to have a separate instrument for every term that is interacted with the treatment. That can be done, but it's a bit harder, and that's why a lot of the more recent applications of fuzzy regression discontinuity designs focus first and foremost on the reduced form, and then present auxiliary evidence on the first stage. And they do this simply because they when you have just a reduced form, you can use the standard techniques that we have with, run OLS regressions with polynomials above and below the threshold. You can do optimal bandwidth selection and so on. But if you want to do all these things in an IV framework, you need lots and lots of data points in order to draw any meaningful inference. That's why we focus typically on the reduced form. Now, rather than deriving how you would do this in an IV framework, let me just show you one of the canonical papers using a fuzzy regression discontinuity design. So this paper is over 20 years old now, but it's still being taught as the standard fuzzy RT. So this is by Angerson and Lavie, and studies the effect of class size on student outcomes. So they have data from schools in Israel, and the way the assignment of class sizes works in Israel is it follows, at least roughly, what's called Maimonides Rule. So Maimonides was a philosopher, a Jewish philosopher, and you can read up on him. He had many thoughts, and there's many writings that came from him, and one rule that he established for the education system was that class sizes in schools should not exceed 40. And there is a good few schools in Israel that by and large follow that rule. So the idea is that if the enrollment of a cohort reaches 41, we split the cohort into 2 classes. But if it's 40 or below, we keep it at 1 class. And then the same happens at multiples of 40. So if we have an enrollment of 79, we have 2 large classes. But if it reaches 81, we would have 3 classes, something like that. So they describe in the paper exactly then what those starting cohorts, how many classes they are split into at different thresholds. But the fact of the matter is there are those thresholds that are important. And you can see this in the actual class sizes. So what they plot here is the class sizes on the vertical axis versus the size of the starting cohort. And you can see here that the actual data is the solid line, and what is predicted by Maimonides Rule would be that's the dashed line. And so you see Maimonides Rule would actually be a very sharp sawtooth pattern here. That's not exactly how it works, but you can also see that the class sizes, they trace this sawtooth pattern pretty well. So you have discontinuities that work, that are adhered to, but not perfectly so. And why? Well, because schools obviously want to use their discretion. They don't want to follow this rule all the time, but by and large they do. So you have imperfect compliance with a rule. Now the assumption here underlying all this is that for schools, it is not possible to manipulate whether they have enrollment cohort or that they have starting cohorts that are just below or above that threshold. Right? They can then decide, do we split the class or not? And some of them may decide we have 41, but we're not going to split them. But they cannot manipulate the number of students enrolling in a school. And that, whether that's plausible depends on the context, but it's typically plausible. Right? So it's not that, it's obviously that the enrollment in a school fluctuates from year to year through natural variation in the number of people with school-age children who live in a neighborhood. And so therefore you have, in some years you're above and in other years you're below. So that is, in my view, a reasonable assumption. And you see here that there is imperfect compliance, but there is some compliance here. Right? So and then what they do is basically they use the predicted class size as an instrument for the actual class size. Now, what we can see here is what they do very nicely here is that they have here on one vertical axis the test scores, so that's on the left, and on the right they have the class size. And so basically what what each of those graphs shows you for different grades is the reduced form. Right? So you have the dashed line here. So this line here, that's the instrument, and the solid line here, that's the outcome. That's the average test score. Right? And so just by eyeballing the data, we can see that we see some sort of sawtooth pattern and changes in the direction at these kink points. And so that's a useful thing to know. Okay, so that is a very good first test for whether we actually should expect an effect or whether the effect is just some statistical artifact. If nothing else changes at those thresholds except for the size of the class and then the number of classes that get formed, why should we expect those strong kinks in the outcome if it wasn't for the class size? So that is very strong evidence. And then what they show is the following. So first of all, they look at, with OLS, they just relate the test score in reading and math to the class size without controlling for anything. You can see this here, and you actually get a positive result. And that is probably a sign of a bias, because we would expect that the smaller the class size, the higher are the test scores. So we would expect a negative sign. Now, why could this be? Well, it could be simply that in places that where students are particularly strong, that's also where they can afford larger class sizes. Okay, so if we compare all the schools, then those schools that have a lot of disadvantaged children, they may choose to have smaller class sizes. But we don't know then, is that the relationship due to the schools choosing to have smaller class sizes, or is it due to those schools actually just having the weaker students? So they show here that the sign flips when you control for the share of students from a disadvantaged background, whatever that exactly means. The sign of the coefficient of class size flips, but it's quite small. And now what they do is they use the instrumental variable estimator, and what they do here is so this is basically the two-stage least squares estimate, whereby the class size is instrumented by Maimonides rule. And what you can see here is, here they use the full sample, and here they use a bandwidth of plus minus 5 in terms of class size. So they only consider classes that are, they only consider cohorts that are 5 above and up to 5 above and up to 5 below that threshold. So if the threshold is 40, they consider between 35 and 45, but nothing beyond that. And you can see here that the effects are much larger, and they're even larger when we zoom into those discontinuities. So this is an early example of basically using IV in a regression discontinuity setting. And a lot of newer work is based on this idea, but obviously there are more fancy techniques out there now to determine the optimal bandwidth and to provide robustness checks, to incorporate different polynomials or non-parametrically controlling for functional form above and below the threshold. This is what you need to figure out yourself when you write an RD paper. The basic idea hasn't changed in 20 years, but what has changed is the standard of evidence that you need to bring to make this convincing. So here I'm giving you some references to some practitioners' guides that are also, from what I can see, regularly updated. one is by Matthias Cataneo and the other by David Lee, who are some of the main people when it comes to regression discontinuity. So they have made significant methodological contributions on that topic. To summarize for now, regression discontinuity is one of the most popular methods, and you can easily see why, because it's transparent and it's easy to explain to non-economists, and you don't have to, it's easier to defend the identification assumptions relative to a standard instrumental variable estimate. But there are some challenges to identification. Because the assumption that units that are just above the threshold, that the potential outcomes of those units who were supposedly treated and the potential outcomes of those units who were not treated because they're below the threshold, that their potential outcomes are the same, and therefore the assignment is as good as random, that is untestable. We can obviously bring evidence and say, okay, let's compare the units above and below along other dimensions, and ideally we wouldn't want to find any differences, but we can never be sure that their potential outcomes are actually the same. And one particular challenge is manipulation. And manipulation is something that may happen, and there is a whole other literature especially in public economics, on so-called bunching, that documents that when people can easily manipulate, for example, their taxable income, you see huge bunching at those thresholds. So you see huge spikes at those thresholds where, if your income is just below 1,500 euro a month, you get an additional unemployment benefit, and then guess where a lot of the incomes are concentrated? Exactly below 1,500. And then, so it depends on the context whether these things can be manipulated, the treatment status can be manipulated or not. If it cannot be manipulated, you're in safe RD territory. If you see huge manipulation in the data, then you should go to a very different type of estimator, namely the so-called bunching estimator. So there are estimators that, let's say, if you have a threshold here, and you see in you plot out not the outcome, but let's say that the density of observations at the threshold, and you see something like a massive spike just below that threshold, and maybe then a trough here, and then it goes back to normal. If that's the density, then there's clearly some manipulation going on, and then it's better to think about the problem in a very different way and think about what can we learn about behavior from the fact that people actually manipulate. And can we model this manipulation, and then can we learn something about the structural parameters underlying people's or firms' behavior? And that literature is called bunching, and is a very large one, especially used in public economics. Okay, so back to manipulation. Now, if there is a little bit of manipulation, there are things you can do. Now, I'm just going to show you here how to detect manipulation. The first and most important technique is eyeballing. Okay, so you just plot out the density of the either the outcome variable or the treatment variable. So here these are finishing times in the marathon, and there is obviously this huge achievement attached to being under 3 hours or under 3:30 or under 4 hours. And so you can very clearly see here that the number of finishers has always these spikes just below those thresholds. It's not that people are cheating in the race, but they're doing, if they have a chance to be below the threshold, they do everything that they can to be below this threshold because it's this particular achievement. And so that obviously, if you see this type of manipulation, I mean, here this isn't exactly malicious, but when it comes to manipulating how much income you put down on your tax statement or these type of things, it might still not be malicious, but it's a problem if you then want to claim that being below and above the threshold is as good as random, because clearly there must be some deliberate behavior behind this type of bunching that you see here. So if the manipulation is small, what you can do is, well, first of all, there are non-parametric tests. So not only should you plot out this density, and you should also plot out this density not only for the outcome variable, but also for other characteristics of those of the units in your sample, and see, is the density smooth or not? If it's not smooth, it's hard to defend why being above or below the threshold is random. Then you can run a so-called McCrary test, which is basically just a non-parametric test for bunching at arbitrary kink points or at arbitrary threshold. It basically just tests whether that distribution is smooth or not based on the data you have. And if there is doubt that there is manipulation, but if you believe the manipulation isn't very big, then what you can use is a so-called donut hole estimator. A donut hole estimator is what it says without the sweetness. So the idea of a donut hole estimator is as follows. You have a discontinuity here, and you have then an area. So first of all, you have your bandwidth. So you have x naught minus delta and x naught plus delta. But then you have also a region in which you believe that manipulation happens. So let's say we believe that in this area we can have manipulation. And so that's x naught plus minus some other parameter, eta, which determines how big that donut hole is. And so what you do is you leave out observations within that narrow bandwidth, that green one, that you leave out the donut hole, and you then only use observations that are within your bandwidth but not within the donut hole. And how this is done in practice is that we typically we would make that inner bandwidth smaller and larger and see do the results change if we do that. So this concludes the part of the lecture on regression discontinuity designs. Once again, it's a very, very powerful method. It's used very often. If you want to use it yourself, my advice is go to papers that have been published recently in top journals and see what they do and how they set this up and what evidence they bring. In the lecture slides that accompany these videos, you also see more tips on how to run an RD analysis. But it's important, there's so many new developments, and it's important to stay up to date, as it is with any other method of causal inference as well.